We're going to talk about in this video is the structure of an atom and the actual bonds between atoms, so either intermolecular or intramolecular bonds, and we'll go through a couple of examples of intramolecular bonds such as covalent bonds and ionic bonds. But what you should know when it comes to the structure of an atom is that when we're talking about things like atomic mass and atomic number, they have to do with subatomic particles, so for example protons, neutrons and electrons. The atomic number, A or Z, is basically just the number of protons. Protons we can always find in the middle or the center of your nucleus. This is your nucleus right here, and in the middle of it we've got protons and neutrons. And the atomic mass is just basically the mass of the atom, so anything that has mass is part of the atomic mass. Now if we look at the actual mass, you're going to find that things like proton is often given the atomic mass unit of 1. We use AMU, which is the atomic mass unit, because it's so small, the weight is so small that we wouldn't use grams, right? Proton has atomic mass unit of 1. Things like the nucleus, or sorry, the neutron. The neutron also has the atomic mass unit of 1. And something like the electron, which is another subatomic particle, electron has a very small weight. So even one atomic mass unit is small, but when it comes to electrons, they're much smaller. So there's quite a few zeros when it comes to after the 1 when it comes to the atomic mass unit. So 0.0001 atomic mass units for the electron or thereabouts, whereas the neutron and proton have a much higher atomic mass unit. So when we're talking about the atomic mass, even though electron does have mass, we tend to not talk about electrons and their mass because it's so small we can kind of ignore it. So the only two subatomic particles that are going to be part of the mass is going to be your proton and your neutron. So atomic mass unit, or atomic mass, sorry, not unit, is basically your number of neutrons plus the number of protons. Those two combined will get you your atomic mass. So if, for example, we have our atomic number given, we can figure out, and our atomic mass given, we can figure out the number of neutrons. Because remember, the atomic number is the number of protons. Atomic mass is neutrons plus protons. So if we have the number of protons given, we know the total mass, we can figure out the neutrons by just removing the protons. So basically, atomic mass unit minus atomic number gets you the number of neutrons in that actual atom. That's just bits about the atomic mass and atomic number. When it comes to things like valence electrons, so when it comes to an atom has as many protons as electrons, because it has to. An atom it has no charge, it's neutral. We know that protons have positive charges and electrons have negative charges. So for something to be an atom, it has to have equal charges. So plus and minus have to be equal. So every atom will have as many protons as it does neutrons. So for example, this carbon atom will have 6 protons and will have 6 electrons. But the electrons that are most important are the electrons on the outer shell. So these 1, 2, 3, 4. These 4 are called your valence electrons. Valence electrons are just your electrons on the outermost shell, and they're going to be the ones that take part in reactions. The other electrons don't take part in reactions. So what you should know is the valence electrons are your outermost electrons that take part in reactions. And when it comes to the two elements, hydrogen and helium, which are these two right here, they only have the first shell almost filled or filled, which means their valence electron are going to be hydrogen only has 1 electron, so it has 1 valence electron, and then helium has 2. Now in the case of helium, its shell is actually full, because the first shell can only hold 2 electrons. So helium is quite happy because all elements or all atoms want to have their shell to be full. So in the case of helium, it's going to be happy because it's going to have a full shell. In the case of hydrogen, it's missing 1 to get to 2, so it's going to be still wanting to react with something else to make it have a full shell at the end. Now lithium has 2 in its inner shell, but remember the ones that are important for reactions are going to be the outer shell, and it's going to only have 1 in the outer shell. Now same with carbon. Carbon has 2 in the inner shell, but remember the ones that are important are going to be the outermost shell. In this case it has 4 in the outermost shell. it will want to have 8. So it wants to have 8 electrons because the second shell can hold 8 electrons. So both lithium and carbon are not happy with the electrons they have because they want to have more or less, whatever it is, to make sure they don't have the perfect number in their outermost shell. Same nitrogen. Nitrogen has 2 in that first shell, which means it's full, and then it has 5 in the second shell, which means again it has 5, wants 8, so it needs to have 3 more to make it happy or make it achieve its goal. Now sodium has 2 in its first shell, it has 8 in its second shell, so that second shell is also full. But remember, the valence electrons are the shell which is the last shell. So in the case of sodium, it has 1 valence electron because that's its outermost shell. And that means even the sodium, even though it has that second shell full, its last shell is not full. So therefore, it has to do something to try to make it have all of the valence electrons filled. Now, the reason why I'm mentioning all this is because if you are in that state where you have electrons, valence electrons not full, the valence shell not full, you're gonna do something called bonding between within a molecule. And so there is something called the intermolecular bonds, which are bonds between molecules, and there's something called the intramolecular bonds, which are bonds within a molecule. So what I mean by this is, if you have a look at here, these are our carbon dioxide. So we have these weak intramolecular between these. Each of these is a carbon dioxide, and we have these weak intermolecular bonds, which are between molecules. These ones right here. But again, they're weak. Examples are dispersion forces. We'll talk about both of those throughout the course. Dispersion forces and hydrogen bonds. But these are relatively weak. We're not going to be talking about them in this video. The ones we're going to talk about are the ones called intramolecular. And intramolecular are within the bonds. So those are these ones right here. These are in the actual molecule, and they're very strong. Right, so if this is a carbon dioxide molecule, these are the bonds we're talking about. These ones here. They keep the actual molecule together. They're not between molecules, they're within the molecule, and they are very strong. And those intramolecular bonds can be called covalent bonds, or they can be called ionic bonds. But we'll talk about more of those in a second. We just talked about the valence shell and the need for atoms to make sure that their valence shell is full. So that could mean that they might have 8 valence electrons if they're, for example, a bigger atom, or 2 if they're hydrogen or helium, but they need to have their valence shell to be full. Now we're going to talk about 2 ways that atoms and ions can do, or can basically bonds that these different types of atoms and ions can perform to make sure that they actually have a full outer shell. And these are going to be called intermolecular bonds, and we'll talk about that in a second. And the first one we'll talk about is the ionic bond. And as the name suggests, it's going to be happening between ions. So ionic bonds happen between ions. And we'll start out with actually showing you how we go from an atom to an ion. What you need to know about atoms is atoms will have so the atom has equal amounts. So it's neutral, which means it has an equal amount of protons plus electrons, because protons are positively charged, electrons are negatively charged. But an atom will always have equal amounts. So in this case, we've got a sodium atom right here. The way we know that, it's got these P stands for proton, E for electron. We know that because it has 11 protons in its nucleus and 11 electrons in the shells around it. So it's going to have equal amount of positive and negative charge, which means it's an atom. Same with its chlorine atom here. At the moment, it's got 17 protons and 17 electrons. That means it is neutral, which means it's an atom. But I'm going to show you how we go from the actual atom to the ion and why that happens. So first of all, let's do the counting of where these electrons actually are. So if we have this sodium atom, at the moment it has 2 electrons in the inner shell. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons in the middle shell, and just 1. So this is its valence electron. It has 1 valence electron in its outermost shell. So just 1. And chlorine has, just like sodium, it's got 2 in the middle, 2 in the innermost, 8 in the middle, and then 1, 2, 3, 4, 5, 6, 7. 7 in the outermost shell. Now, are any of those atoms at the moment happy? No, they wouldn't be, right? Because they want to have 8 valence electrons, or at least they want to have an outer shell that's full. and that outer shell in this case has to have 8 electrons. Now what's going to happen is we're actually going to find that this atom right here, the sodium atom, will give this electron to the chlorine atom. So, and then they will become ions. So that's going to happen. You're going to have this actual electron being passed over to the chlorine atom. And I'll do that now. So I'll just show you how it's passed over. So I'm going to rub it out, this part here, because that actual electron will have gone over. Alright, so how many does this actual chlorine have now? So it's got 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 valence electrons now, as opposed to 7. So it used to have 7, now it has 8. So that means it has a full shell. Its outermost shell is full, so it's going to be quite happy. Now, what's going to happen also is it used to have 17 electrons, and now it's actually going to have 18 electrons. So what that means is it has one more negative charge than positive charge. So that's 17 positive and 18 negative. If you do 17 minus 18, what you're going to find is you're going to have one minus left. So you're going to be not neutral anymore. You're going to have one extra minus. So we just put that as chlorine minus, as opposed to just chlorine. And if it's chlorine minus, that means now it's an ion. Ions are charged. Are going to be positive or negative? This chlorine ion is negative. Now we said that the actual sodium has lost this electron. So as opposed to having 11 electrons, it's lost one. So it's going to have 10 electrons. Protons don't change, but overall, if you have a look at it now, it has 10 electrons. It has 11 protons, so it has one more proton than electron, which means one more positive charge compared to negative charge. So this, we don't call it sodium anymore, we call it sodium plus, or Na plus, because this is now also turned into an ion. So anything that has plus or minus is an ion. This is a sodium ion, because its charges are no longer balanced. But why does the sodium want to lose an electron? Well, we'll talk about that now. So it had one valence electron before and it was not happy because the shell was not full. But the easiest thing for a sodium atom to do, if it only has one electron, is it gives that electron away, because what happens then is the whole shell goes away because there's no electrons left. This is not the outermost shell because there's nothing left. And that leaves it with the next shell being its outermost shell. And if you have a look at how many electrons there are, this shell is actually already full. It has a full shell now too. So if the sodium gives away its one electron, that means its last shell is full, and it's actually going to be quite happy. So we tend to find that the sodium atoms tend to become ions to give away the last remaining electron, then to also have its shell be changed to this valence shell, but this new valence shell is actually full, so they're both happy. So in this case, ionic bonds occur to make both atoms have full valence shells. Both the sodium and the chlorine will have full valence shells, but they will no longer be atoms, they will actually now be ions. And what's going to happen is this positive charge and this negative charge are going to attract, because opposites attract. So these two will attract, and that means once this bond actually happens, or once this whole thing happens, these two will then stay together. So sodium and chlorine will be attracted together, and these will no longer leave each other. And that's what we call a ionic bond. And it happens between these opposite charges. Alright, so that's an ionic bond, and they occur, and they're in intermolecular bond because they occur between two actual atoms that then become more or less one. And the other one that is an intermolecular bond is a covalent bond. Now, break that word down. Co means basically together or cooperate, so they are going to work together. Valent talks about your valence electrons, so it comes from valence electrons, and it's going to be a bond. So they're going to make a bond to share their valence electrons. And the example here is your two oxygen atoms. Now we said that ionic bonds occur between ions, whereas covalent bonds will always occur between atoms. So we're going to have neutral atoms involved in covalent bonds, whereas ions are part of the ionic bonds. Alright, so we have two oxygens. They're both going to have the same amount of protons and electrons, right? 16 protons, 16 electrons for each, because they're both atoms. They're going to be neutral. Now where those actual electrons are, right, so we've got 2 in the innermost shell because that's full already. We'll have 8 in the next shell because that's full. And then we've got 1, 2, 3, 4, 5, 6 left. 6 for this oxygen atom, and same for this one, 2, 8, and 6. So at the moment they both don't have a valence shell that's full. They both have 6 in their shell. They want to have 8. So what can they do? Well, in this case, all that's going to happen here is we're actually going to have the middle ones, these two, come closer together, and they're going to share those valence electrons. So 2 are being shared from here, 2 are being shared from here. So in total, in the middle, we're going to have 4 that go both ways. So these 4 count for both the atoms that are between that bond. So if we do the new count, we had 6 beforehand. Now we have 4 here in the middle. 5, 6, 7, 8. So now this actual oxygen atom now has 8. So it's going to be happy. This one again, those 4 get shared both ways. So 4, 5, 6, 7, 8. So again, not going to be 6 anymore. Also going to be 8. So now their shells are going to be full. Their valence shells. Both of these oxygen atoms are going to be completely happy. So that's why this occurs, because they basically make sure their shells become full, and the best way to do that for these would be to do covalent bonds. So it's basically oxygen plus oxygen goes into oxygen gas, or O2, and remember these are all atoms, they're not ions. And this is just the Lewis dot structure of how this happens, so that's called the Lewis dot structure. And so we see these are going to be shared between both, so it's going to be accounting for 4. Then we've got 5, 6, 7, 8, 8 for this one, 4, 5, 6, 7, 8, 8 for this one, and both of them are happy. And this is your conventional way of showing it, but that just means that there's a double bond in the middle. So that means every one of those lines is 2 electrons being shared, but they share 4 in total, so that's why we have a double bond. That means 4 being shared in total. Right, and now the last thing I want you to know is ionic bonds occur between metals and non-metals. So one of them is going to be a metal, and it tends to be your one that loses the electron is going to be a metal, and the other one is going to be your non-metal. So for example, sodium is a metal and chlorine is a non-metal. So ionic bonds tend to occur between metals and non-metals, whereas covalent bonds tend to occur between non-metals. So they tend to occur between non-metals. An example here are oxygen, O2, which is a non-metal. Both of them are non-metal. Carbon dioxide or any of those are all between 2 non-metals. But the reason why I'm doing it is the same, to make sure that I have a full valence shell.